have a full complete set of data, including the inputs being the features and the expected outputs. And in the context of our example here, in the insurance dataset, the inputs would be the demographics of, or the characteristics of each customer, being the gender, BMI, age, and so on. And the output is the insurance charge. What we're trying to do here in this supervised machine learning exercise is to understand the patterns that each feature of the customer contribute to the outcome, or the value of the outcome being the insurance charge. So we have already done a small exercise of building a model when we plotted the scatter plots of each individual feature. Again, it's the output or the insurance charge, and we came up with a function that captures the relationship between each feature and the related output. But we emphasized and highlighted that this is by no means a valid model or valid regression model, because of what we will be understanding next in this video. Let's recall what we have done previously. We have built a model here that captures the relationship between each numeric feature and the related charge, or the related output being the insurance charge. And we've said that each model has a set of parameters. The first parameter is being called the intercept, and intercept is the value of charge or the output or the dependent variable when all other features are being 0. And the other parameters are being the estimates or coefficients of the relationship between the dependent variables and the related charges. There are some set of terminologies that we need to agree on. A feature or a predictor or an independent variable all relates to the same thing. And in the context of insurance exercise we're doing here, they are the characteristics of each customer. For example, age, gender, BMI, and so on. Dependent variable or target value is the amount that we are interested in estimating and predicting. And in the context of insurance exercise, it is the insurance charge. So dependent variable is the insurance charge, and independent variable are all other features of the customer. We are actually gonna build an ordinary least square regression, and ordinary least square regression simply tries to figure out which line that best fits the data, and the best fit here is calculated or assessed in terms of the difference between the line and all other real data points. So in order to understand this, let's imagine that this line is the line of best fit, and it represents the predicted value of charges given different value of age. So for example, if we have a customer that is having age of 50, we would project or predict that its related insurance charge will be around 15K, for example. So at each X value, we predict the related Y value, which is charges, given this line. And of course, we can see here that there is a difference between the actual points or the actual customers having, for example, age 50 and the line. So this distance between this point and the line is referred to as error or residuals. We will understand what's the difference between error and residual, but for the time being, note that the best fit line is the line that minimizes this distance so that predicted values represented by this line are as near as the actual values. In order to understand OLS better, let's take a look at this figure. Imagine that the y-axis is the insurance charge and the x-axis is, for example, age. Each data point represents the corresponding age and related insurance charge. So for example, let's say for example it's age 10 and the related insurance charge is 3, C is like 15 and insurance charge is 1, and so on and so forth. Just ignore the scale and focus on the points and this line that's rotating up and down. Now, we said that each line represents a function, and this function captures the relationship between the feature or the predictor or the independent variable and the dependent variable. The best fitting line or the line that OLS solves is the one that minimizes the distance between the line and the red dots being the actual data points. So this dashed line between each actual data point and the line is the error term, which is basically the difference between the actual data points and the predicted data points. Predicted data points, or predictions in general, are in fact the line. And this is actually a really important concept to understand. When you plot a line through the data points, this line is the model that captures the relationship between these features. So this line as is the best fitting line. When it starts to rotate, we can see that the difference between each data point and the line sometimes is exaggerated. For example, in this, it is smaller than this. And when it starts to rotate again, you can see that now they are all equal. And when it rotates, see here for C, for example, it's way more than A, and now it's in A way more than C, and so on. So in general, an ordinary square captures the relationship that minimizes the distance between the actual data points and the predicted line. And the least square here is the least difference between the line and the actual data points. And when we start to discuss the math behind linear models, we will understand what are these squares and how do this line come up with such equation or solution for the linear system. Now, how to build a model? There are actually several ways to build a model, and there are several modules that we can use to build a model, but we have previously used statsmodels. So what's happening here? We are actually instantiating a model using sm.ols, and we are passing the dependent variable being charge and independent variable being age, and in this case we are using only one feature, and adding constant. Adding constant facilitates the calculation, and we will see how does this actually help. Then dot fit, and we said that dot fit is where the calculation happens and the coefficients are actually calculated, or the estimates are calculated. Fit is when the function is being generated or estimated. If you want to see the results of this model, we can store it in a variable called model, then call model.summary. Now we can see here the result of the linear model. Let's first start by this portion here. It's self-explanatory. Here states the dependent variable being charges and the type of regression used, method least square, date, time. Total number observation is the total number of samples that's used to calculate in the model. DF residual stands for degree of freedom residuals, and it is basically the number of features used in the model subtracted from the total number of observations. So we can see here we have one parameter being age and another parameter being the constant or the intercept. If we subtract these two parameters from the total number of observation, we get the 1336 samples. And we can here see a degree of freedom model. It's basically the number of actual features that are used to come up with the estimates of the model. So what's the difference between degree of freedom residual and degree of freedom model? Degree of freedom residual accounts for all the parameter in the model, including intercept, while degree of freedom model just accounts for the feature that is used in the model. This portion actually tells more about the regression quality. We can see here R squared, it's an indication of the goodness of fit, and adjusted R squared is actually the same as R squared but takes into account the total number of features used. So we basically look for adjusted R squared that is equal to or almost equal to R squared. This means that the results of the model is somewhat robust. Of course, a low R squared means that this model is actually not good, because R squared is the percentage of variance that this model helps to explain in the dependent variable. So this model explains about 8% of the variance in charges. This is actually very low percentage. We can't actually rely on age only to understand the change in the values of charges. This is the p-value of f statistic, and it actually is a small value which denotes that this value is statistically significant to rely on, which means that there is actually a variation in charge value when the feature of age is used. The most important part of this table is this middle section here, where we get to see feature used, the related coefficient, and coefficient is the estimate of a change in the dependent variable given a change in independent variable. So for example, we say here that for each 1 unit increase in age or 1 year increase in age, we expect that dependent variable or charges increase by 257. The sign of the coefficient indicates whether there is an increase or decrease in the dependent variable giving change in the independent variable. So if this was negative 257, we say that for each increase in age, we expect that dependent variable decrease by 257. So we here see the coefficient and the p-value of the estimated coefficient. And as we discussed, p-value indicates whether what we're seeing here is significant or not, and in this case it states that age is actually significant in predicting the dependent variable because it is a low value. Linear regression is actually a sort of statistical test. The null hypothesis is that there is actually no relationship between the dependent and independent variable, and the alternative hypothesis is that there is a relationship between the two variables. So what we can come up from this small model is that age is somewhat significant in predicting the dependent variable being charged. However, by itself, it is not good at explaining the variance in insurance charge. And by logical thinking, we actually do not expect that age alone justifies or explains why would an insurance charge differ from one customer to another. If we want to assess whether the results of this regression reliable, we need to confirm that the assumptions of linear model is actually being met. There are actually several assumptions of linear model, and we are going to discuss them in detail. The first assumption and the most obvious assumption is the existence of a linear relationship between the two variables being measured, dependent and independent variable. And linearity here refers to the parameters of the model. Any linear model consists of a independent variable referred to as y, and in our case here it will be the insurance charges, okay, equal the intercept, and the intercept here is the amount of y when all other parameters of the model are equal 0. So if we take this model for example, and we assume that y in the insurance charge is a function of intercept plus age, okay, so intercept is the value of y when age is equal to 0. Age in this term is referred to as the slope, and slope is basically the amount of variation in the dependent variable that is expressed or explained or expected by change in unit of a dependent variable. If you write the equation in mathematical notation, it will be y equal ax plus b, for example. And here a is the coefficient or the estimate of the linear model, x is the age, and b is the intercept. So when we say linear in the parameters, it means that y needs to be a function of a linear combination of these parameters, and not that the independent feature is actually linear. We can express x or age in terms of x squared, for example. So it's a polynomial or an interaction of x and another feature, let's say gender, for example. So this is one assumption of the model. Another assumption regards to the residuals. And we have discussed that residuals are actually the difference between expected value or the predicted value and the actual value, and we can extract the residuals from the model. So we say model.resid, and it spits out the differences between the actual and the predicted value. And if we want to understand where did this actually come from, let's generate predictions using our model. So model.predict df age, and let's assign the constant. These are actually the predictions given the age feature. So for example, let's look at the data frame. For the first sample, it predicts that charges is 8k, while in fact charges is actually 16k. So the difference between the predicted value and the actual value is 8k, and this is what we see here in the model.residual 8.8k. We can actually calculate the residual ourselves without extracting it directly from the model by simply subtracting the actual from prediction. So df.charges minus the prediction, and we will get the exact same output. We understand now that residuals are the difference between the actual charges and the predicted charges. And one of the assumptions of a linear model is that residuals are normally distributed. So if we come to the residual and plot it using a histogram, so sense.histplot, we need to see a normally distributed residuals. So we can actually see here that it is not normally distributed. So we have a violation in one of the assumptions of linear model. Another assumption of a linear model is that variance is homoscedastic, and homoscedastic is a fancy word of equal variance. What does equal variance mean? It means that simply the predictions need to be equally distributed across the fitted line. If you want to assess a homoscedasty assumption using visual method, we can regress the predicted value to the actual value and observe how does these values are different across the line. So for example, we will use a sense.resid plot. So resid plot actually regresses y on x. So we will basically feed it with the predictions, and we will use the predictions to make an estimate of charges and observe the variance around the fitted line. So our x will be model.fitted values. Fitted values are the predictions. This is a residual plot. We actually use predictions from the model to estimate the charges and observe the distribution of data point across the line. Here it's used a standardized residual, so we here around 0 is our model, and each points represent the distribution of the residuals along the line. We actually want to see an equal distribution of values around the line, and this can actually be noted here. So for age, we can say that residuals are not normally distributed but have equal variance. We can say that residuals are homoscedastic. So we have up to now a violation in the normality of residual assumption. Another way to assess whether residuals have equal variance is through using a statistical method. There are two statistical tests that are used to assess the homoscedasty of residuals, being Heter-White and Bruch-Pagan. So run these tests. So we can see here 4 different statistics and p-value. We are actually interested in the p-value. You can see here that it is not significant, which means that we can reject the alternative and accept the null. And the null in this test is that variance is actually homoscedastic. So there is an equal variance among the fitted values. If we use a Bruch-Pagan test, we also get the same results, that it is not statistically significant to reject the null, and we assume that no homoscedasty issue exists. So what if we changed age to use BMI, for example, but we need to actually change this in the model itself? Let's use BMI. You can see here that R squared is lower, still F statistic is significant, and the coefficient is larger here than age. And we can see here also that there is a skew, but it's slight skew in the residuals. If you recall, skew is a measure of skewness of a distribution, and we said that the rule of thumb it's between -1 and +1. Anything above that means that the distribution is not normally distributed. We can see here that okay, it's almost normally distributed apart from this tail here, and if we run our tests, we can see that it is significant, and this means this -26 means this number is very small. There is 26 zeros before this number, so the p-value is actually significant and it favors the alternative against the null, and we can conclude that there is a homoscedastic issue, which is referred to as heteroscedasticity. And so we say that the variance is heteroscedastic, and in a simple term, it means that the variance is not equally distributed. If you use the Bruce-Pagan test again, change to BMI, we can also see that it gives the same output. Now, if we want to look at the residual plot, so we can actually see here that the distribution at both sides of the line is not equal. It fans out. Here we can see a V shape, which means that at this area the variance is smaller, but as predictions increase, the difference tends to increase. And this is a classic case of unequal residual values. It means that our prediction will be accurate at this area, but as the amount of charges increase, our predictions tend to be actually wrong. Another good property of this resid plot is the ability to include a Loess curve. This line passes through the most deterministic part of the data that captures the variance in this setup. So for example, in BMI, this lower portion of the data points is the most deterministic part where the variance is properly captured. And if you recall that this part represents non-smoker groups and this upper part represents the smoker group, so it is basically telling us that if you want to use BMI as a single predictor, if you use it on the two type of smoker group, it will fail to capture the trend in both groups. So this suggests that it might be better to split the data into two portions, being either smoker or non-smoker group, and fit separate regressions for each group. We have been through a lot and we need to summarize what we have actually done so far. So first of all, we have built a model using ordinary least square regression, and that the most significant area is this, where we calculate the coefficients of each feature. The easiest part is to build a model, but the most important and critical part is to assess whether this model is actually valid or reliable or not. We learned several assumptions of linear model, being first of all existence of linear relationship, and assumptions related to residuals being normally distributed and have equal variance, which is also referred to as a homoscedastic relationship. And we saw how to assess each of these assumptions. We used the skew score here to test whether residuals are normally distributed or not. Then we have used the statistical method to assess whether a homoscedastic relationship exists in the residuals, and we use also visual methods to assess this homoscedastic relationship visually, and we use different type of plots. What's left next is just basically trials with different models until we reach to a model that first of all satisfies our understanding of the data. We know from our previous analysis that age or BMI alone are not sufficient in understanding the variance in charges. So we need to build a more robust model revolving around other different features. And at the same time, we need to ensure that our model meets the assumptions of a linear model so that we can rely on the estimates. Next, we will see how to build different models and how to assess each model using the method we used so far. But before we move on, let's understand what does it really mean to have assumptions not met yet. How does this affect our model? If linear assumptions are not met, the model can still be relied on, but the p-value or the estimates are somewhat not reliable. So what does this mean? This means that I want to build a model to explain the relationship between BMI, for example, and charges. So I need a model that measures this relationship and enables me to express it in numerical terms. So I want to say that for each 1 unit increase in BMI, I expect a 300 or almost 400 increase in charges. If the model assumptions are violated, this means that I cannot actually rely on the calculated estimates. So I can say that there is a relationship, and for each increase in BMI there is corresponding increase in charges, but I will not be as confident as quantifying this relationship if the model assumption were met. So if I have a violation in assumptions, it doesn't mean that I throw the model away, but I'll just not be as confident in the calculated estimates. Let's build models using different features or combination of features and test these models and assess whether we have a good model or not. So we'll start by building a function to collect some of the calculations that we want to make. So we will name our function res visualize, regression, residual visualize, and this function takes in data frame, columns, and also a target value. So on target value we will keep it as empty string. Okay, so we want our function first to build a model. So model equal statsmodel.ols. we will pass in the df and target. We will also pass df, as we will pass the columns in a form of list, so we will keep it as columns, assign constant equal 1 and dot fit. Okay, then we want to print model dot summary. Okay, then plot model dot residuals. Okay, lastly let's print the calculated statistics. So and let's make the sep to be a new line. So sep new line means that it will print each on a different line. Now let's run this cell. Okay, target. The error just means that I've missed a square bracket. Let's test our function. So it will be res visualize, and we will pass df, all the numeric columns, and our target to be charges. So this is our model. Each numeric feature is presented, the related coefficient and the p-value. We can see that all are actually significant. The overall r squared is 12 and the adjusted is almost 12 also. However, this whole model does not explain variance in charges well. This is one thing. Another thing, we still have problem with normality assumption, residual normality assumption. It is somewhat skewed, and we can see here that it is heteroscedastic, as the p-values are significant, so there is actually unequal variance issue with our model. So regarding the fixes for the model, we can try different things. First, we know from our early analysis that what might work with this data is that we split the data into two groups, smoker and non-smoker. So let's first do this. And now let's redo our model. So we can see a significant increase in the model. In general, r squared jumped from being 12 to almost 75. We can also see that f statistics is increased, significant f statistic, and the coefficients are also changed. And we can see here that BMI is becoming the most significant feature, while children actually does not affect charges much for smoker group, because the p-value of a related statistic is actually 0.5. And the model is not suffering from the problems of the residual normality assumption or the equal variance assumption. We can here see that residuals have equal variance, are homoscedastic, and that they are normally distributed. So by understanding our data and making simple changes in our model, we are actually able to obtain a better and robust model than what we have seen earlier. We will close this subject as this, and hopefully we now understand what building model that captures pattern in data. And the most preceding or important aspect of this is that you understand your data and you already identify some of the patterns that you expect the model to capture. And when it comes to modeling, you need to understand what are assumptions of this model and whether this model meets the assumption or not, so that you can rely on the model estimates. Next, we will discuss how does linear model actually comes up with such estimate, how are coefficients calculated, and how does linear model in general actually work. I have an in-depth project built on this dataset where I explore different versions of model and different methods of handling assumptions violation, so I encourage you to check it there. So see you next video where we discuss the mathematics behind linear model.